Have you ever pondered the mysteries of the universe and wondered about the enigmatic black holes that reside within it? Now you might be wondering, what exactly are black holes? Contrary to what the name might suggest, black holes are not empty spaces. Quite the opposite, in fact. They are a great amount of matter packed so densely into a small area that they create a gravitational field so powerful that nothing, not even light, can escape its pull. Imagine the weight of a mountain compressed into a tiny pebble. That's how dense we're talking about here. But how did we come to know about these celestial anomalies? The existence of black holes was first predicted by none other than the great physicist Albert Einstein. His groundbreaking theory of general relativity, formulated in the early 20th century, paved the way for the scientific understanding of these space-time curiosities. According to Einstein, when a massive star exhausts its nuclear fuel, it undergoes a dramatic collapse under the force of gravity, and a black hole is born. Interestingly, despite their name, we can infer the presence of black holes by studying their effect on nearby matter. You see, matter near a black hole gets sucked in due to its immense gravity, often forming a swirling disk as it spirals inward. It's like a cosmic whirlpool, if you will. Black holes come in different sizes too. Stellar black holes are typically 10 to 24 times as massive as our sun, while supermassive black holes can be millions or billions of times more massive. And guess what? There's a supermassive black hole lurking at the heart of almost every large galaxy, including our very own Milky Way. So black holes are indeed a celestial wonder with their immense gravity and enigmatic nature. But how do these fascinating celestial objects come into existence? To answer that, we need to venture deep into the cosmos, where the life cycle of stars plays out. Picture a star that's more than 10 times the mass of our sun. It's burning hot, radiating light and heat into the universe. But this stellar giant's life cannot last forever. Eventually, it exhausts its nuclear fuel. Without the energy to counteract the force of gravity pulling inward, the star collapses under its own weight. This catastrophic event triggers a supernova explosion, the death throes of a massive star, outshining entire galaxies for brief moments in time. But what remains after this cosmic spectacle? The core of the star, now crushed to an infinitesimal point of infinite density. This is the birth of a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape its pull. Now, black holes aren't all the same. They come in different sizes, each with their own story. Stellar mass black holes, for instance, are the remnants of massive stars, typically 10 to 24 times the mass of our sun. But there's another type, far larger and more enigmatic: the supermassive black holes. These celestial behemoths are millions, even billions of times as massive as the sun, and they didn't form from a single star. Instead, scientists believe they might be the result of a chain reaction of star collisions in compact star clusters, or perhaps they formed at the same time as the galaxies they inhabit. Every large galaxy, including our own Milky Way, is thought to harbor a supermassive black hole at its heart. These cosmic giants play a crucial role in shaping their galactic homes, influencing star formation and guiding the evolution of galaxies. Therefore, black holes are born from the remnants of massive stars, a testament to the incredible forces at work in our universe. Does the existence of black holes pose a threat to our Earth? This question has stirred the imaginations of scientists, writers, and curious minds alike. Black holes, with their immense gravitational pull, have often been depicted as cosmic vacuum cleaners, ready to inhale all matter that strays too close. But is there any truth to this portrayal? Black holes, for all their mystery, are not the cosmic predators they're often made out to be. They don't roam the universe, hunting down and consuming celestial bodies. Rather, they stay relatively still, anchored by their own gravity. Like any other body in space, they move, but not in a way that would cause them to suck up planets or stars that aren't in extremely close proximity. Yes, a black hole's gravitational pull is strong, so strong that not even light can escape. But this pull doesn't extend infinitely into space. If our sun were suddenly replaced by a black hole of the same mass, the Earth's orbit would remain unaffected. We'd be plunged into darkness certainly, but we wouldn't be drawn into the black hole's gaping maw. The Earth is simply too far away to be in any immediate danger, and before you start picturing rogue black holes hurtling through space towards us, it's important to note that space is vast, mind-bogglingly so. The nearest known black hole is about 1,600 light-years away. That's nearly 10 trillion miles. For a black hole to pose any real threat to Earth, it would need to be much, much closer. So, while black holes are incredibly powerful, we need not fear them swallowing our planet anytime soon. Their threat, it seems, is more to our understanding of the universe than to our physical existence within it. They challenge our knowledge of physics, space, and time, pushing us to learn more, to explore further, and to continually question our place in this grand cosmic tapestry. What wonders or horrors could we find inside a black hole, if we could venture within one? This question has intrigued scientists for decades, sparking a multitude of theories and hypotheses. Now imagine stepping into the unknown, a realm where our current understanding of physics is pushed to its absolute limit, and perhaps beyond. This is the bewildering world that lies inside a black hole. One of the most prevalent theories suggests that at the heart of each black hole is a singularity, a point where all matter is squeezed into a space so infinitesimally small that it essentially has no size. It's a concept so mind-boggling that it's hard to fully grasp. This singularity is believed to be of infinite density, a place where gravity is so incredibly strong that it distorts space and time itself. But here's where things get even more interesting. Our current laws of physics, as we understand them, break down when we try to describe what's happening at the singularity. This is because our knowledge is based on Einstein's theory of general relativity, which describes the universe on a large scale, and quantum mechanics, which explains the behavior of particles on the smallest scales. However, these two theories are incompatible at the singularity, creating what scientists call a singularity problem. This problem is one of the biggest unsolved mysteries in theoretical physics. Some researchers suggest that a quantum theory of gravity, a still elusive theory of everything, could solve this paradox. Others propose that singularities might not exist at all, and that black holes could instead house quantum fuzz, a state of matter governed by both gravity and quantum effects. It's important to note that these are just theories. As of now, we lack the technology to peer inside a black hole and verify these speculations. So, the inside of a black hole remains largely uncharted territory, a cosmic riddle waiting to be solved. The insides of black holes remain a mystery, a frontier where our current understanding of the universe falters. But as we continue to probe the cosmos, who knows what future discoveries may lie in wait? After all, isn't the allure of the unknown one of the driving forces behind our quest for knowledge? Will black holes forever remain a part of our universe, or will they too, one day vanish? In the grand cosmic drama, even black holes, those insatiable devourers of matter and light, might not be immortal. Enter the concept of Hawking radiation, a theory proposed by the legendary physicist Stephen Hawking. This theory posits that black holes aren't completely black, but emit tiny amounts of thermal radiation due to quantum effects near the event horizon. Now, picture a pair of particles, a particle and its antiparticle, spontaneously popping into existence near the event horizon. One of the pair falls into the black hole while the other escapes into space. The energy needed to create these particles is borrowed from the black hole itself, and as the escaping particle carries away some of this energy, the black hole loses mass. This phenomenon, known as black hole evaporation, could lead to the slow and steady demise of a black hole. However, we're talking about a timescale so vast it defies human comprehension. For a black hole with the mass of our sun, we're looking at a lifespan of about 10 to the power of 67 years. That's a 1 followed by 67 zeros. But what happens when a black hole finally evaporates completely? Well, we're not entirely sure. The laws of quantum mechanics suggest that the information about everything a black hole has ever swallowed is preserved and encoded in the Hawking radiation. However, how this information gets out or what it could tell us remains a mystery. Just as they are born, black holes too will one day cease to exist, leaving behind only echoes of their once formidable presence.